have all set, and we move on forward to visualize components. We have 3 components. You can see component 1, 2, and 3. You can name them, but we can leave it as it is. And let's go to component 1. You see the red lines there that marks the component. It's floor. Then the second is the ceiling. You can see it here. And the third component, these are walls. You can see with the red and orange lines. Let's move to component 1. And, we have the inner side and outer side. Inner side will set boundary conditions for that, for simulated zone. And for outer side, I'll choose the outer air. For now, WUFI will take the climate data, but we'll override it with our constant temperature. We go to assembly, and this is the time we need to define material that will be for our cube side or floor as you want it. To make a material, you go to database, click on materials, and all the database opens up. There is plenty of materials predefined with different properties already built in WUFI, but we need a new material and we need a phase change material. So we click on new, and we name material like lesson material. Then we enter data for our assumption that sensible heat is much smaller than latent heat. We just enter density, density 1, heat capacity 1, thermal conductivity 1, and then water vapor diffusion resistance factor. I'll also put 1, but we actually don't need it, as we won't calculate humidity. Typical built-in moisture, also of the same reason, we actually don't need it. Porosity, I'll put something very small here. Okay, that's about these data. Then there's optional data that is different coefficients and their dependence on temperature or moisture or whatever. What we need from this is an enthalpy, and this is needed for to define phase change. We click new, and for 0 degrees we'll have 0 enthalpy. For gas new 22, that's the temperature where the phase change is going to happen. I'll put something in 1000. You see already the function is drawing itself. New 22.1, and I'll put a huge amount here, like 1 with 7 zeros. So we have a step. That's the phase change from 22 to 22.1. That's the phase change, and you can see a huge leap here. And then we enter a new one from 30 degrees and something small. And here you go, the last part. It's actually not flat, but it's a little bit changing. But compared to latent heat, this change is very small and can be neglected. That's our approximation, and it works. Another thing is optional. It's typical thickness. I'll put in 0.3. This is important because of that I don't have to type it in manually for each component. So I press OK, and we have a lesson material here in our library now in database, and I close the database. Next, I double click assembly. I'm on component 1 here on the tree. I double click and add new material, lesson material. Here it is. We apply, and we have a 0.3 meter thick phase change material here. Okay, and we are fine. We have defined for the flow. We have defined material. Next is surface. There are two things. First is heat transfer resistance, and that is for both for inside and outside the environment. There are two values. If those values are real values, then there is third type boundary conditions here, because there is additional thermal resistance on the boundary layer. I'll change them by switching to user defined and typing 0, so we have a first type boundary condition. Then also this will not affect the result. If there were a third type boundary condition, the problem would be a little bit different, and the results would be affected. No, they won't be. Next, solar absorption, and I put zeros here. Then I get rid of solar gains that is, and well, it doesn't affect results. We don't need the moisture tab because we are not calculating it. What we need is a climate on outer surface, and this we want our predefined 30 degrees Celsius, and so we select our sine curves outside. Initial conditions is very important because we have a solid that will melt, and so I put in 22 just below the temperature of phase change. And mode of calculation, moisture transport calculation, but it's checked, but it wouldn't have calculated the moisture anyway, because on that case we had a thermal calculation only. Okay, let's go back to component, and we are fine with component 1, and we can go to component 2. Once again, in general, there's nothing much to change. In assembly, there's already available assemblies, and I just double click it so it assigns 0.3 meters phase change material we made previously. Surface, the same thing, optional climate, sine curves and outside, nothing in moisture. Here we change to first type boundary conditions. Okay, and no solar gains. It's fine. Initial conditions, once again, it's very important. 22, and we are fine with component 2. Component 3, the same thing. Double click. User defined. 0 and 0. 0 and 0 and 0. We are eliminating all the good things WUFI developers have put in there, but well, we need that. Climate, optional climate, and outside 30 degrees Celsius. Initial conditions 22 degrees Celsius, and it's fine. Okay, not visualized components we don't have. Such internal loads, we don't want any internal loads, so we because it will change the heat balance, and therefore will make additional fluxes that will affect our results. We don't want it, so we leave it empty. Design conditions. This one is important. I will put 22 degrees inside, and minimum and maximum also 22, just below the phase change temperature. We are fine. Excuse me. Yeah, the same is about humidity and CO2, but we are not calculating them, so we leave them empty. Next is ventilation. We don't want our air inside the box changing, so we type in zeros here. But, natural ventilation means filtration, and for mechanical it's by default 0. But check if it's really a 0 here. Okay, this is fine. We don't have air exchange affecting our one-dimensional exercise. For other parameters, it's the initial temperature inside, and I'll put 22 degrees, so the air temperature inside the box doesn't affect things. And so radiation direct to indoor air also 0. Okay, no attached zones, nothing here. We go to HVAC, and we need something to heat the room. What we need? This is because there will be melting going on. Okay, we click new because we need the system for heat, so the balance stays and system 1. Next I click on system 1, and for this system there's new for heating and cooling. We have a system, we want space heating, and we want space cooling. We go to device and enter capacity. By default it's 50 kilowatts, and the cooling capacity is also 50 kilowatts. But it will take for calculation as much as it needs, not 50 kilowatts. So it's fine. We leave it as it is. It's very much. And I have forgot we go to component, and here we must check retain calculation results in report data and results tab. We click on it. That's so we could export the results after we have finished calculations, and do it for all the components. It will take some extra memory, but it will help us in the future. We are all set. We can start the calculation. So for this, there is a start button here. I click it, and it calculates. And you can see here, when we component that it slowly melts. You can see it's 12% done already. When the phase change will be over, it will get much faster. We have our cooling unit set up, and also heating unit, but we'll need only the cooling unit because outside temperature is higher than inside. So after the material melts, the cooling unit will turn on. Okay, and we are ready. I click on the start button here. Let's go to component first. Okay, and click on start, and it starts to calculate. And here you can see the picture, like how it's happening. At first it's melting very fast, and then the process slows down. While the phase change is happening, we saw that there was a high jump in enthalpy, and well, it's important that you understand that the steeper the jump, the more difficult it is for numerical model to calculate. So it's traveling really hard. It will be faster after the material melts. And you can see how far it has melted already. Because temperature here is 22 degrees Celsius, and here you can see this is the wall cross section. You can see here, and it's temperature here. And, it will be done quite soon. And the reason why it's so becoming more slower in the end, it's because the thermal resistance of this part is increasing. There's thermal conductivity lambda that is equals to 1, and then here are heat fluxes. As you can see, in this wall there's heat flux. Some kind of heat flux, and then there was not, but now it melted down, and now it's the jump when everybody has melted, and now it's a stationary process going on here. You see that up here. Well, yeah, we actually do have some kind of thickness, and when the temperature cutoff was like this, then the thermal resistance was only for this part, and the conduction happened only this far. As it got to that end, there's a thermal resistance much larger, and so the whole wall is better insulated than just part of the wall. Okay, we are halfway done, and I'll stop for a while, and you'll see me after the calculation has done. Also, an important feature here I have changed the axis. But you'll have access like in component 2. You can see from negative 20 degrees Celsius to 40 degrees Celsius, and you can change them here. Enter the minimum, like 20 degrees, maximum, like 32 degrees, and increment of 2 degrees, click OK, and you see the temperature, the axis value is changed. Then now you can better see the temperature profile here. Okay, it has finished now, and we can go to our components, and we can see the heat fluxes, and I click on heat fluxes, and here you can see, I'll zoom them in, like this. You can see that the red one is the heat flux on the outer surface, and the blue one is the heat flux on the inner surface. You can see that it starts from like 1.6 kilowatts per square meter on the outer surface, and very rapidly drops to reasonable values. And for inner surface, there is no heat flux, and then at this point something happens, and there is heat flux. And well, why is that so? Well, at this point, you see, there is a matter has melt, and there is a sudden jump in inner surface heat flux, and the heat is starting to flow out of the inner